generic names of most cephalosporins start with a Ceph prefix that is spelled either with F or PH. They are divided into first, second, all the way to fifth generation. This classification is based on the time they were discovered. With the more knowledge gained about the structure-activity relationship with every modification, cumulative enhancement of a spectrum against the gram-negative bacteria and resistance against beta-lactamases is seen when moving forward through generations. In terms of protein binding, there isn't a pattern seen that correlates it to structure, as seen with penicillins. Thus, you will not be required to predict variations in plasma protein binding based on structure. Consider this table as a reference for the pharmacokinetic properties of cephalosporins. If any information regarding acid and metabolic stability and resistance to beta-lactamases is not discussed in the text in later slides for any of the cephalosporins we'll be covering, refer to this table. This table lists all the different substitutions on position 3 and the alpha and beta substitutions on carbon 7 for all the discussed cephalosporins. Before we start discussing the different members of the generations of cephalosporins, let's discuss in detail the effect of the variant substituents on carbons 3 and 7. Now, the nature of the substituent on position 3, as discussed before, affects mainly acidic and metabolic stability, which are reflected on oral bioavailability, thus the possibility of the drug to be given orally. There are a few exceptions that we will encounter later, but generally speaking, having a good leaving group attached to position 3 via a carbon will facilitate the easiness of breaking a beta-lactam in acidic conditions, which will render the cephalosporin unstable, thus orally inactive. What dictates a leaving group being good or bad is its relative stability. The more stabilized, the better the leaving group will be, and you can determine that stability based on two factors. The atom that the developed negative charge will be on, the more electronegative, the better. The larger the size of that atom is, the better, and more importantly, delocalization via resonance. In terms of metabolic stability, a cephalosporin with a methylene acetoxy or any other group that, when metabolized, will give a methylene hydroxy or hydroxymethylene will be considered metabolically unstable. Now let's apply what we've discussed already on the following group of cephalosporins. When R is a proton, methyl, chloride, methoxymethylene, or alkenyl, these substituents are not considered leaving groups to begin with, or they are actually very bad leaving groups upon beta-lactam hydrolysis. To understand this, let's apply the elimination mechanism on the 3-methylcephalosporin as an example. If you remove electrons when breaking the beta-lactam, what needs to be eliminated is a hydride in this case, which is a very bad leaving group because simply hydrogen is a small and a very weakly electronegative atom. Now, a chloride is, relatively speaking, a good leaving group, but in this case, it's directly attached to carbon 3, and similar to the hydride, it doesn't have empty orbitals to accommodate the developed negative charge. In the case of the methoxymethylene, the leaving group in this case would be a methoxide. Now, it is true that oxygen is a good electronegative atom, but the charge in this leaving group is localized. So based on all that, cephalosporins with such substituents are considered acid stable, thus if absorbed well, they would be orally active. The alkenyl is not an ejectable group, as we've already established, but relative to a cephalosporin that has a methyl, for instance, its liability to hydrolysis and consequently potency are more. The reason behind this is that the conjugated double bond will further delocalize the developed charge as seen in these resonance structures, thus enhancing the stability of the broken beta-lactam. Now, in regard to metabolic stability, none is an acetoxymethylene, thus they are all metabolically stable. Cephalosporins with methylene acetoxy are both acid and metabolically unstable. Carbamoyl cephalosporins are also acid unstable. A carbamate, similar to an acetate, is a good leaving group since the developed charge on it will be delocalized between electronegative atoms via resonance. As for the metabolic stability, would you consider a carbamate easily hydrolyzed by esterases, as in the case of the ester? Now, the answer to that depends on the electrophilicity of the carbonyl carbon. In a carbamate, nitrogen does withdraw electrons from the carbonyl carbon inductively, but at the same time, it donates electrons via resonance, which is a more profound effect. This renders the carbonyl less electrophilic, thus more stable against esterases and their metabolic effect. Cephalosporins with 3-thiothiazole, N-methyltetrazole, 3-thiotriazine, pyridinium, and pyrrolidinium are not subject to hydrolysis by esterases, thus all are metabolically stable. They are good leaving groups, which make them unstable to acidic conditions. The reason behind the stability of the leaving groups in thiothiazole, MTT, and the triazine, as you see, is the electronegativity of the atoms sharing the developed charge that is delocalized via resonance. Methylpyrrolidine and pyridine are the best leaving groups because when eliminated, they are neutral. Substituents attached to carbon-7 mostly affects the antibacterial activity and resistance to beta-lactamases. An amine at the alpha position of the acyclic amide, similar to penicillins, enhances the acid stability. Yet, as we've discussed before, it's actually the nature of the substituent on carbon-3 is what determines the acid stability. A methoxy at carbon-7 increases the stability against some beta-lactamases due to steric hindrance. Yet at the same time, they induce production of other isoforms of beta-lactamases. These cephalosporins are collectively called cephamycins. Another structural feature that leads to enhancing stability against beta-lactamases is having a substituted enzyme such as methoxyamine, N-alkoxy acid amine, or a substituted alkene at the alpha position of the acyclic amide. There is a huge difference in resistance among the Z and E stereoisomers of these rigid double bonds. The E almost does not pose any resistance to beta-lactamases. You can easily determine the stereochemistry via assigning the priorities of the substituents on each of the atoms of the double bond. If both are on the same side, it would be the Z stereoisomer, while if not, this will make the E stereoisomer. What I will do starting from this slide on is similar to what we've done when discussing penicillins. We'll cluster members of each generation and determine their stability in acid against esterases and beta-lactamases. Regarding these members of the first generation cephalosporins, cephalothin, cephaloridine, and cefazolin have good leaving groups. They are acid unstable, thus not orally active. While cephalexin, cephradine, and cefadroxil have a methyl at carbon-3, thus they are acid stable and can be given orally. That methyl, though, will not aid in stabilizing the hydrolyzed beta-lactam when broken by transpeptidases, which will render these compounds less potent. The only cephalosporin that will not be stable against esterases is cephalothin. Thus, it's metabolically unstable, the rest are stable. In terms of resistance to beta-lactamases, none have a methoxy at carbon-7, nor a substituted alkene or oxime on the alpha carbon of the acyclic amide, so all are sensitive to beta-lactamases. The main generalization that we can make regarding the first generation cephalosporins relative to their penicillin counterparts is that they are poorly absorbed and they have lower binding affinity to the target penicillin binding proteins. Another natural cephalosporin is cephamycin C. This compound was isolated from a culture of Streptomyces claviligorus, which is a bacteria, and this makes Cephomycin C the first beta-lactam to be isolated from a bacterial source. The interesting structural feature in Cephomycin C is the methoxy on carbon 7, and these cephalosporins are called cephomycins. This increased resistance is thought to be due to the steric hindrance provided by the extra methoxy group. Another semi-synthetic modification that resulted in stability against beta-lactamases is the methoxyamine or methyloxime group. These cephalosporins are called oxaminocephalosporins. The following structures represent the cephalosporins classified being second generation. The ones that we can classify as being beta-lactamase resistant are those with a methoxy at position 7, cefoxetine and cefotetan, or having a substituted oxime or alkene at the alpha carbon, which are cefuroxime and cefuroxime acetyl. The rest are sensitive. In regard to carbon 3 substituent, in cefoxetine, the urethane, which is an ester bioisoster, is considered a good leaving group, thus making it unstable to acid. An exception to the generalization we are following is cefuroxime. Although it has a urethane, yet its acid stable and can be given orally, and the oral bioavailability can be further enhanced with the acetyl prodrug. Now, the exact explanation for this exemption is not well understood. Cefaclor and loracarbef are acid stable, since the chlorine being attached directly to carbon 3 will not facilitate the opening of the beta-lactam, thus it's orally active. MTT is a good leaving group, the cefotetan is not acid stable. In cefprozil, though the alkene further stabilizes the developed charge on the nitrogen upon hydrolysis, yet not to a point where it will be acid labile, so it's stable in these conditions. Loracarbef is considered a bioisoster of cefaclor, where the sulfur is substituted with a carbon. Now, the reason behind such modification is explained in the next slide. Cefaclor is not chemically stable in plasma due to what is known as aminolysis, where the alpha nitrogen, being nucleophilic, attacks the beta-lactam, deactivating it. It is believed that the electronegative sulfur, being electron withdrawing, contributes to the electrophilicity of the beta-lactam. Thus, when substituting the sulfur with a carbon, which is much less electronegative, this will increase the stability of the beta-lactam against the nucleophilic attack of the alpha amino group. Thus, loracarbef is chemically more stable in plasma than cefaclor. Now, the carbacepheme in loracarbef is not biosynthesized by microorganisms. Thus, different than the rest of the cephalosporins, loracarbef is obtained via total synthesis. Structurally, the third-generation cephalosporins are characterized with having on the side chain an oxime, a substituted oxime, or a substituted alkene, which make them stable to beta-lactamases. The sp2 hybridized alpha carbon is attached to an aminothiazole ring instead of the phenyl bioisosters seen in the second-generation cephalosporins. This ring is believed to enhance the penetration of cephalosporins through the outer membrane of a gram-negative bacteria and may also increase the affinity for transpeptidase enzymes. As a result, third-generation cephalosporins containing this ring have a marked increase in activity against gram-negative bacteria. The size of the oxime or the alkene substituents would vary the degree of beta-lactamase stability. For instance, the stability in cefotaxime is better than that of cefdinir. The bulkier side chain in ceftazidime leads to more pronounced beta-lactamase stability and a greater affinity to transpeptidases in many gram-positive strains. Also, the additional ionizable carboxylic acid leads to increased permeability through the porins, thus a greater anti-Pseudomonas aeruginosa activity. As for the acid stability, the general rule of being stable if the group on carbon 3 is a poor leaving group applies to all, with the exception of ceftriaxone. The exact reason behind the acid instability, although it doesn't have a leaving group, is not known. Cefotaxime is the only cephalosporin in this generation that is metabolically unstable. Cefpodoxime proxetile is a lipophilic prodrug that was developed to enhance the parent's drug oral bioavailability. Even though cefpodoxime is acid stable, yet its absorption does not exceed 50%. The vinylic hydroxyl in thiotriazinedione is acidic with a pKa that approximates that of a carboxylic acid due to stabilization of the conjugate base via resonance. Thus, this drug is formulated as a disodium salt. The two drugs that are classified as fourth-generation cephalosporins that we will be discussing are cefpirome and cefepime. Both have the methoxyamino aminothiazolile as the C7 side chain that results in resistance to beta-lactamases. The permanently charged substituents on carbon 3 results in enhanced penetration to gram-negative bacteria, thus leading to broader spectrum of activity. Both groups are good leaving groups, thus the cepheme is susceptible to acidic conditions and can only be administered parenterally. The first FDA-approved cephalosporin that is classified as a fifth-generation cephalosporin is ceftaroline fusamyl. Notice the complexity of the substituent on carbon 3. The 2-thiazolile spacer that links the permanently charged methylpyridinium to the cepheme ring was optimized for its anti-MRSA activity. This group enhanced binding to abnormal penicillin binding proteins, such as penicillin binding protein 2A expressed in MRSA. This drug has the widest spectrum of activity relative to all lower-ranked cephalosporins. Similar to what is seen in the third and fourth generation cephalosporins, the alkoxyamino group maintained resistance to beta-lactamases, and the 1,2,4-thiodiazole ring maintained the activity against gram-negative bacteria. Now, ceftaroline lacks sufficient water solubility for routine clinical use as a parenteral antibiotic owing to its zwitterionic structure. To overcome this solubility barrier, ceftaroline fusamyl prodrug was developed by attaching a phosphate group to the 1,2,4-thiodiazole ring. The prodrug undergoes dephosphorylation by plasma phosphatases liberating the free ceftaroline.